So let's do this question. These survival renewal questions are really just kind of an example of identify the things and then throw them into the formula. So let's read the question. The drug is administered intravenously at a rate of 10 milligrams per hour. So the rate coming in is your R of t. The patient eliminates the drug over time so that the proportion remaining is e to the negative 0.25 t. So that's your S of t, the survival rate, the proportion remaining. And then if the patient currently has 70 milligrams in their system, by the way, that's going to be our P naught, the initial amount we have. I guess I can underline that. How much will there be in 8 hours? That's going to be our capital T. So we've identified all the things that have to go in the formula. Then we have to, I'm not going to pretend like I remember the formula. We have to look up the formula, write it down, and then plug everything in. So I've already got it on the other side. Planned ahead. So there's our formula. P of t, the amount of stuff at time t, or the population at time t, right? How much has survived, renewed, whatever, is equal to S of t times P naught, integral from 0 to t, S of t minus t R of t. So again, right, this P naught here is 70 milligrams, and capital T is 8. So just plugging those in first, P of t is going to be S of 8 times 70 plus the integral from 0 to 8 of S of 8 minus little t, R of t, dt. And then I actually plug in what the functions are, right? We know that R of t is real easy here. R of t is just 10. That's about as easy as it gets. And I forget, S of t was e to the negative 0.25 t. Okay, so we're going to throw it in. So S of 8 is going to, I feel like I've made a, no, that's fine. I just, let me, now I feel like let me verify one thing real quick. Sorry, I feel like I'm making a stupid error. I don't want to make a stupid error. Let me see one thing. Sorry, you guys can fill in the next part if you want. I was like one page away from it. Ah, that's okay. Yeah, I did make it. I made a small mistake. It's not a huge mistake, but this should be. Let me double check. Yeah, sorry. This should be P of capital T here. I was kind of thinking like, so I was thinking like, I know I'm supposed to be calculating how much stuff I have at time equals 8, but I'm not seeing where I'd plug in 8 over here because it should be P of capital T, which is P of 8. Sorry about that. So we're getting population time 8. So S of 8 is going to be e to the negative 0.25 times 8, which is e to the negative second, right? Negative 0.25 is negative a quarter, times 8 is negative 2, times 70, plus the integral from 0 to 8. So S of 8 minus t, this is the part that probably have to be a little more careful on. So that's going to be S of 8 minus t is going to be e to the negative 0.25 times 8 minus t, which is looking like e to the negative 2 plus 0.25 t. Or as I would probably write it, e to the negative 2 times e to the 0.25 t. That seems like the best way to write it. So that's what I write here, e to the negative 2 times e to the negative 0, sorry, positive 0.25 t. So many things to write. And then we also have the R of t, which is just 10 dt. That's not too terrible. I mean, it's not nice, but it's fine. This is going to be, I'm going to write this as 70 over e squared. I'm going to pull out these constants. So I'm going to have a 10 over e squared And then the integral of e to the 0.25t is going to be e to the 0.25t divided by 0.25 from 0 to 8. So that's going to end up giving me, let's see, 70 over e squared plus 10 over e squared times, and then plug in 8. So by the way, dividing by a quarter is multiplying by 4. So when I plug in 8, I'm going to get 4e squared minus when I plug in 0, I'm going to get 4 times e to the 0, which is 1. And I would probably stop there. I mean, we could keep going. It's going to be 70 over e squared. When you distribute this, 10 times 4 is 40. The e squareds cancel. Distribute this, 10 times 4 is 40 over e squared. So, oh, sorry, minus 40 over e squared. So if you wanted the final answer, you could say it's 40 plus 30 over e squared milligrams of the drug. But I would say the real kind of thing to take away from these survival renewal problems is that there are 3 things you have to identify. 3 things? 3 things I think you have to, maybe 4 things you have to identify. You have to figure out what time it is at the end. Okay, they're usually going to tell you that. You have to figure out what your survival rate is. They're going to tell you that. You have to figure out what your, I guess that's the renewal rate is also, which, I mean, they're going to tell you all the things. You just have to be able to identify them and put them into the formula. Well, and then you have to know how much you start with. But that's, I mean, it's, yes, the formula is not nice, but it's very much, here's all the pieces, put them into the integral, and then calculate stuff. It doesn't seem like it's much more complicated than that, even though the integrals might themselves be somewhat complicated. Okay. Are there questions about this? Make sure my volume's on before I say are there questions. I think my if you're trying to say something, my volume was off. So are there questions about this? I erased the other side. So I did want to talk about, I feel like it's pronounce this, but I don't know how to pronounce it. So let's take a look at the other thing someone asked me about, Poussin's law, whatever it's called. And instead of trying to write a bunch of stuff on the board, Grant has a handout that I think is really well written, which I will also, everyone, here's the link if you want to look at it on your own. I'm also going to share my screen and just kind of walk you guys through it. Because I do think it's like, it's weird to just use a formula if you don't really know where it's coming from. So let's walk through where it comes from. Let's see, where is my share screen button? There it is. Share my screen. Okay. I don't need all this other stuff up there. Move you over here. All right. So blood flow. I'm really going to read most of this, but I will stop for questions and explain things to the best of my limited ability. Also, let me make sure the chat is. The problem when I share my screen is it like closes the chat. So I'm like, where's the chat? Oh, there's the chat. Okay. So the velocity v of blood passing through a blood vessel of radius r and length L at a distance r from the central axis. So right, the radius of the blood vessel is r, and the blood itself is traveling at a distance of r from the central axis, where P is the pressure difference between the ends of the vessel and that Greek symbol, which I think is new, but I'm not sure. That N looking symbol, let's just call it N, is the viscosity of the blood. And so the formula for that is the velocity at this distance r from the central axis is the pressure divided by 4 times the viscosity times the length times the big radius squared minus the little radius squared. And that formula is just kind of given. I think it does. So thinking about this again, not knowing a whole lot about fluid dynamics in general, right? It makes sense that the higher the pressure, the greater the velocity would be, the greater the viscosity, the slower the blood would flow, the greater the length, the slower the blood would flow. And then the bigger the difference between the radii would mean the blood would flow faster, right? So if this is a big number, it's going to flow faster. If these are closer to each other is going to be slower. So actually, I mean, I would say that particular thing I'm saying doesn't seem super intuitive to me, right? So like, I guess what this is saying is the further out from the center you are, the slower the blood is flowing, right? Because then big R squared minus little r squared will be closer to 0. So the blood that's right next to the wall of the vessel is flowing kind of slow, versus the blood in the middle is flowing as fast as possible. Interesting. Let me look there. In fact, that is noted down here. The maximum blood velocity is in the middle of the vessel. Great. So now let's scroll down a little. To calculate the rate of blood flow, or flux, which is the volume of blood per unit of time, we need to integrate, which means just add up all the fluxes over the cross sections of the vessel where the velocity is equal. So this is kind of, right. So no, that's not a good example. There's an example I was going to use, but it's not something we've talked about. So what we're going to do is we're going to think about saying, well, all of the blood flow like in this ring is essentially equal because all the blood flow in this ring is at the same radius from the center. So that all that blood in that rectangle, in that circle, can be straightened out to look essentially like this. It's a rectangle of length, circumference 2 pi r, and height delta r. Again, stop me if you have questions, right? Like I'm happy to say more about things if you have a question about a thing. Right? This is just the whole, like we do every time. We use like an approximating rectangle to find the area. We add up all the rectangles. Here we're using approximating circles because each circle, the blood is traveling at the same velocity, right? The closer to the middle, the faster the blood. But since all of the blood in this circle is the same distance from the center, it's all going at the same velocity. So the flux is the volume of blood passing through the region over a fixed amount of time. So it's the velocity of blood times the area of the thin ring, right? That's how we're going to figure out how much blood there is. It's how fast it's going times the area it's going through. That's your velocity times this thing we just set up here, which is 2 pi r delta r. And then you integrate, which you can, so lots of these things are constants, right? The only thing that we're actually integrating here is like the little r squared. So we're factoring out this p over 4nl constant and the 2 pi, and we're just left with the big r squared times little r right there, minus the little r squared times r, which is r cubed. We integrate, we get this, we plug in big R and 0 to get r to the 4th over 2 minus r to the 4th over 4. So when we finally get down to it, after calculating this thing, Cuset's law says that the flux is equal to this gross number here. Pi times the pressure times the radius of the vessel to the 4th power divided by 8 times the viscosity times the length of the vessel. Do you need to know this derivation? I don't think so. Do you need to know this formula? Probably not. You might need to look it up on occasion. It would be hard for me to imagine anyone expecting anyone to memorize this. Like that just seems ludicrous to me. So that said, there's the formula. So what can we do with this? Well, we can look at this next question. And I suppose I could write things down if you guys want me to write things down. So let's look at this question and then we'll figure it out ourselves. Okay. So this is from section 6.3, number 10. High blood pressure results from the constriction of the arteries. We know this. So the heart has to pump harder to maintain a normal flow rate. If R naught and P naught are the normal radius of a blood vessel and the normal pressure of the artery, and the constricted values are R and P, then for the flux or flow to remain the same, we need the following. We need that the new constricted pressure divided by the regular pressure is equal to the constricted radius divided by the regular radius to the 4th power. Now, this seems like, where is this coming from? This is definitely given in the problem, but let's talk about how they're getting that. I think I'll stop sharing now. Okay, so let me stop sharing. Let me take a sip of water because I'm thirsty. So here's where we're getting that formula from. So again, Cuset's law says this, that the flux I'm sure I'm saying that wrong, by the way, is pi times the pressure times the radius of the vessel to the fourth power divided by 8 times this funky looking n. I feel like that's eta. I'm not positive. I've never been super great knowing all my Greek letters, and that's definitely one of the ones I'm not great at. But what we're saying is we want the flux to be equal to each other, right? We're saying that, well, sorry, I'm just let me read the question again. For the flux to remain the same, we need that equation. So for the flux to remain the same, we need the pressure radius with the constricted one to be the same as what you get the flux being when the pressure and the radius are the initial values. But everything else is the same, right? The viscosity of the blood is the same, the length of the vessel is the same, that's it. So you can see like a lot of this stuff's going to cancel out, right? You can divide both sides by pi, you can multiply both sides by 8, you can multiply both sides by eta, you can multiply both sides by L. So you get that P times R to the fourth equals P naught times R naught to the fourth. And then you can divide both sides by R to the fourth. And you can divide both sides by P naught. So that we get, in fact, P over P naught equals R naught over R to the fourth power. So that's where they're getting that from. It's not too terrible to get. So now the interesting question. If the radius of the blood vessel is reduced to 3/4 of the original size, how is the blood pressure affected? Okay, so again, remember what's what here, right? The R naught and the P naught are the initial radius size and the initial pressure. So I'm reducing my new radius R to 3/4 of the initial radius. So we're basically saying R is equal to 3/4 of R naught. Okay, let's see what happens when we do that. So if I plug in 3/4 of R naught, well, the R naughts cancel. Dividing by a fraction, you flip and multiply. So that's going to be 4/3 to the fourth power. 4 to the fourth is 16 squared, which is 256. And 3 to the fourth is 81. And that's definitely more than 3. That's maybe about 3.16. I don't know that off the top of my head. I'm looking at the notes. But I do know it's bigger than 3. So then look what that means. That means that the pressure, if we multiply both sides by P naught, that means the pressure is more than tripled. So if you reduce the blood vessel radius by 1/4, right, reduce it to 3/4 of the original size, then the pressure is increased by more than 3 times as much. That's a huge effect. And important to be aware of when you're an old man like me. Blood pressure is a thing you should actually be aware of for your health. Okay, so that's all I've got for Poiseuille's law. Again, I feel like I'm just totally butchering it. Poiseuille, I don't know. Anyway, if you have more questions about this, I'm happy to try to talk about it. But as I imagine you guys can kind of see, I don't know a whole lot about it. We've got these formulas. We can manipulate them. But that's kind of about it. All right, someone did send me a copy of the test. So let me take a look at it. People had questions about 1A and 1C. Let me just grab those. Sure. Cool. Yeah, okay, we can take a look at this. Hopefully you guys found, I feel like the practice we did last week was helpful. Yeah, okay. Let's look at 1A and 1C. And then I've got other questions people ask me too. Oh yeah, there was actually, one question I want to address because I couldn't figure it out. So I'm going to put this up here real quick just because somebody asked about this, but I feel like it's missing a piece. And I can't figure out what piece is missing. It seems like it has to do with even and odd functions, but it didn't say if anything was even or odd. So the question that somebody asked was, if we're given that the integral from 0 to 1 of f of x dx equals 10, we want to find the integral from -1 to 1 of x squared times f of x cubed. And the problem I'm having is it feels like we need another piece of information to do this. Like we need to know that the function might be even or odd. So if there's something, if whoever asked this knows what I'm talking about and knows that there's another piece of information, let me know. Otherwise, I don't know if there's a way to, I don't know how to do that problem without more information. Okay, sorry. So
I think, sorry.
Go ahead.
Ask that question. And I think it was even.
Okay, that makes total sense to me then. So let's actually do this one like real quick because it's actually not too bad. The thing to recognize here, or the trick kind of here, is to see that it's a u substitution. We can definitely do a u sub because look, we've got something stuck inside another function and its derivative is right there, or close enough to its derivative is right there. So we could let u equal x cubed. And then du is equal to 3x squared dx. So 1/3 du is x squared dx. Also, I should write down, right, the f of x is even. Okay, yeah. So then if we start replacing things, x squared dx becomes my 1/3 du. F of x cubed becomes f of u. Not gonna lie, I used to think that was kind of funny when I was a student. Back then I was like, oh, f of u, okay. And then if x is 1, u is also 1 cubed, which is 1. If x is -1, u is -1 cubed, which is also -1. But I really want everyone to be super clear. These are x values, these are u values. They just happen to be the same because u is equal to x cubed. But then the function f is even, meaning if you go from -1 to 1 or negative whatever to the same whatever, this is going to be equal to 2 times the integral from 0 to 1 of f of u du. And don't forget about the 1/3. And then we're done, because we know that the integral from 0 to 1 of f of u du is the same as the integral from 0 to 1 of f of x dx. Right? This integral and this integral are literally the same. They just have different variables, which means this is 10. So our answer is 2/3 times 10, which is 20/3. But yeah, the key to a problem like this is recognizing there's a u substitution that you have to do before you can do anything else. Yeah, I think so. I mean, I'm trying to think. Maybe there's another way you could do it. I don't think so. I think we're stuck doing this. Okay. Back to the practice, not the practice, the short exam 2 questions 1A and 1C. We'll look at those. I've got one other thing, and then I feel like we should probably spend a little bit of time talking about the stuff from class today, which was differential equations. So here was 1A. The question was to find the integral from a to b of x times f prime of x dx. And we're given a lot of things. We're given f of 0, f of 5, f of a, f of b, integral from a to b. Wow, okay, so let's see. So here's what we know, which it's a lot of stuff to write down. So we know f of a equals 2, f of b equals, where'd you go? This might be a hard problem, or at least hard to think of at first. From a to b of f is equal to 3a. Yeah, okay. That's all I feel like we need at this point, but I don't actually, oh, yeah, I don't know. All right then, let's see. So here's my intuition. I don't actually know. My intuition is that we have to do integration by parts here. Because I see something that derivative looks nice, and definitely we know how to find the antiderivative of f prime, it's just f. So without any other kind of ideas, I'm going to say u is going to be x, dv is going to be f prime of x dx, du is dx, and v is definitely f of x dx. F of x, sorry. So then we can rewrite this as uv minus the integral of v du. This is from a to b, this is from a to b. Okay, yeah, that actually turns out really nice. So then, right, for this part here, we're going to get b times f of b minus a times f of a. And then this part here, we're going to get the integral from a to b f of x, which someone told us was 3a already. So f of b is 4, so I get b times 4 minus f of a is 2, so 2 times a minus 3a. So it looks like we get 4b minus 5a, which I don't think we know anything else about, so I'm going to leave it like that. Yeah, that's a funky question. I mean, it's not a bad question, but it's definitely like, I've probably never seen a question like that before, really. Interesting. Let's look at C as well. Yeah, so, okay. We can do C right here, I think. Let's go this side. Okay. Sorry, it's always hard to decide. I don't know if we're not. So C was finding the derivative of the integral from 1 to x cubed of x cubed plus, t plus b over t plus c dt. Okay, so derivative of the integral is the function, but we know that when it's a more complicated thing like that, we have to use the chain rule. So what we're going to get is we're going to get x cubed going in for every t, right? Because that's the variable that this integral is actually in. So we're going to get x cubed plus b over x cubed plus c times the derivative of x cubed, which is 3x squared. So I think that's your answer. I don't think there's anything else to do there. Yeah, that's it. There's no plugging in.
I was so confused because it felt so easy. I ended up with that, but it only took me like 5 seconds. I was like, no way.
I agree, Chang. Like looking at it, like especially compared to the other problems, right? Where the other problems you're actually having to do some evaluation for this one, but this one is purely right. It says take the derivative. That's how we do it. So it's good to be a little bit like untrustworthy of your results if you're not sure. But then when you look back, you're like, nope, I did what the problem said. That's it. Okay. Yeah, there was one other. Yeah. Someone asked me about a specific integral in office hours today that I just wanted to make sure everyone had seen at least once. This integral, 1 over e to the x plus e to the negative x, can be a little bit tricky if you've never seen it before. It literally involves a trick, and the trick is the following. You have to multiply by e to the x over e to the x. And someone asked me, like, how do you know to do that? And the answer is someone showed me before, right? Like no one really knows to do this until they've seen it from someone else. Otherwise, you're just kind of like, I don't know. But then if you do this, look what you get. You get the integral of e to the x over e to the x times e to the x. You could write e to the 2x, but I'm going to write e to the x squared. And e to the negative x times e to the x is e to the 0, which is 1. And then we can do a lovely u substitution. We can let u equal e to the x. Our du dx is e to the x. So du is e to the x dx. So then, if we start replacing things, there's your du. And there's our u squared plus 1. And the antiderivative of u squared, 1 over u squared plus 1 is the arctangent of u. And then we plug back in and we get the arctangent of e to the x. So that's a good one to have seen. It comes up every once in a while. And it's just like, oh yeah, there's this thing we have to do. This is often the method I employ when I kind of run out of other things. Like if I see something kind of like this, I'm like, well, maybe I need to multiply by e to the x. Or if it's something like if someone changes the powers a little bit, it's like 1 over e to the 3x plus e to the negative 3x. I'm going to multiply everything by e to the 3x, top and bottom. So just be aware that kind of trick is out there. Okay, let's move over to, I feel like we also could still talk about volumes. We got 15 minutes, so let me, decisions. I say, I'm confused at what type of questions were these. Which ones, Carissa? You mean the one I just did here?
Oh no, I was asking about the other ones because I was like, when I first saw them, I was like, what were they testing? Like I was confused because we've never done them. Like, well, we did similar ones, but not with like, oh, you have to like you have a key and then.
Yeah, I definitely feel like this one is not too out there. Like we did one very similar. The only difference I feel like about this one is like, right? If I were asking a question like this, I might have written it as the derivative of the integral from 1 to x cubed of t plus 5 over t plus 7.
Yeah, because I understood that one because I think we did one similar in like the prep session we did. Because that's why I knew like what the thing was. Like the other ones, I was like,
Yeah, I mean, I will say like this question to me also looked confusing at first. So when something looks confusing, that's when I just kind of go back to, okay, what methods do I have available to me? I suppose I should have at first looked at but the problem, and I agree, the problem here is that it's confusing when they're just like, right, it's just a function name, right? It doesn't say like, it's not asking you to do an actual integration by parts problem where you are writing it as, something like the integral of x e to the x right there. It's like, oh yeah, I'm making integration by parts. But they've tried to make it, I don't know, it's, yeah, I see what you're saying. I don't know if I have a good answer, because this is not the way I would imagine writing a question really at all, because it feels way super general. Let me see, let me look at one other thing here. Yeah. But it feels strange to be using integration by parts or use substitution dealing with kind of functions that are just placeholder functions. Unfortunately, that's what we were given. I don't know if I have a better answer for that. We could also look at problem B for just a second if you wanted to. Although I feel like this one is meant to be the most straightforward of them. If you're doing the integral of the derivative, we should just get the function from 0 to 5. So I'm pretty sure part B was meant to be done this way. And then you're going to get f of 5 minus f of 0, which is going to be negative 3 minus 6. But I suppose what this means for me is that before short test 3, when I come up with a practice test for you guys, I'll try to make some questions that are a little more, I don't know what the word I'm looking for is, but a little more kind of generic in there, not having specific functions, just being like testing more on I would say this question is more a test about the concept, right? It's not really about your ability to actually integrate by parts. It's about your ability to recognize that this looks like an integration by parts problem. That's not the answer I want to have, but it's unfortunately the answer I think that's true. Okay, let's talk a little bit about, sorry, the words, differential equations. Which often gets abbreviated as diff EQs. We are going to be solving differential equations in this class, I think, anyway. If not this class, definitely the next class. And they're kind of a big deal. Like, definitely a lot of what we're going to be doing in 17, the rest of 17b and 17c revolves around how differential equations work, what their solutions look like, how we solve them. So these aren't going away, as I'm trying to say. Definitely get used to having to deal with these. Where'd you go? There are lots of types. Thank you. I mean, yeah, concept-based. That's probably a good way of describing what I was trying to say. So as Professor Burke was saying in class today, there are different types of differential equations. There are the pure time, where you have something like dy dt equals just some function of time, which, right, these are the ones that are probably pretty easy to solve. Because if you've got something like, let me use red here, if you've got something like dy dt equals t squared plus cosine of t, the way you solve something like this is you just integrate both sides, right? To solve this, you do the integral of dy dt dt equal to the integral of t squared plus cosine t dt. And as long as this can be integrated, you just get y equal to the antiderivative of this, which is t cubed over 3 plus sine of t. So the pure time differential equations, super easy to solve. You're literally just anti-differentiating both sides. And it doesn't matter if it's t or if it's, dy dx is some function of x, or what she was writing in class, like d star d cloud is equal to a function of the cloud. That was kind of fun. I don't know why. Right. So pure time, basically, the thing you're differentiating with respect to is what the derivative is equal to the variable that the function of is on the other side. And then we have autonomous, which is probably spelled wrong. It's okay. That's where you have something like dy dt is a function of y. Or often we will see something like dn dt is a function of n, like, sure, like 5n. In fact, we have already seen solutions to this differential equation. So this is the differential equation that describes exponential growth or decay, right? You're saying the rate of growth of n, the number of things we have, is 5 times the number of things we have. That is exactly how exponential growth works. So, right, the growth rate is a function of the population. Solving these types of differential equations is a little more work, which we might not be there. I mean, we're close to there, right? So I'll just point out, we're not going to solve this one, but I'll point out that when we solve differential equations, you need all the same variables on the same side. So if I were trying to solve dn dt equal to 5n, I would, well, I'm integrating still both sides with respect to t. Yeah, so I would, sorry, maybe I'm getting a little ahead of myself. Basically, I would put my n's on the left and my t's on the right. meaning I would divide by n, and I would multiply both sides by dt. And then we would integrate both sides. So just as kind of, because this is going to happen a lot, just so you're aware, when we're solving differential equations, before we kind of do any integrating, we always want to make sure all of the same variables are on the same side. So if we have n's and t's, we want all the n's on the left, we want all the t's on the right. Or if we have y's and t's, we want all the y's on the side where dy is on top, we want all the t's on the side where dt is on top. So you never want your differential d whatever to be on the bottom before you integrate. And then finally, there's the non-autonomous, which is a mixture of both the top and the bottom thing. So non-autonomous, right? This is where you have like your derivative of your thing is a function of both the function and the variable that's the function of. These ones are usually the more complicated ones. So you have something like dn dt, just very basically equaling 2n plus 3t. Most of the differential equations we will interact with in this class are, she said first order, which is true. And there's really kind of two types we're going to see. They're called separable, which are these kinds, where you not specifically autonomous, but where you can bring all one variable to one side and all one variable to the other side. That's the best kind. It's super straightforward. Like, yeah, separable, we love it. And then there's another kind which she'll probably cover, which are called first order linear. And if we cover those, we'll definitely talk about them. What else do I want to say before we are out of time? Oh yeah, she was doing some examples that I thought were good about how you actually show something is a differential equation. So someone asked a good question in class, which is how do we solve differential equations essentially, or how do we find the things we're plugging in? And the answer was, not surprisingly, we're going to learn that, right? Solving differential equations. I mean, solving differential equations is a whole field of study in mathematics. Like there are lots and lots of differential equations that are challenging, if not impossible to solve. But yeah, it's a whole thing. We're going to learn just a couple of very specific types of differential equations that we will learn how to solve. But there are definitely, if you want to learn more about that, there are other classes you can take to learn more about that. I think there's a Math 27B, I want to say, is solving more differential equations. I'm not positive about the number on that, but there are definitely other ones you can take. I had some good examples here. Where'd you go? I thought I had an example here. Oh, sure. Darn it. I wanted. One sec. I know I have a good example here. Always. Yeah, I want that. No, I know what I want. I want that. Sorry, this is less than ideal. But I know I have an example here. I just need to find it. So I'll point out the other hard thing about differential equations is they are not always easy to come up with. And I thought your book had better examples, but I'm not seeing them. So let me grab the 16-day book because I know where these are. You guys are like, okay, fine, James. I apologize for my lack of preparedness on this. Wow, I apologize for my ability to not be able to use a book. Well, what the heck? I really thought there were some differential equations in this textbook, and I'm not seeing them at all. That is kind of weird. I'm sure I'm just missing it. Anyway, sorry. So the problem is I can't come up with an example for this without looking in the textbook because they are hard to just make up. Fine. Okay, here's one from the textbook. So verify, I feel like she did this one in class. No, I don't think she did actually. So verify that this y equal to negative t cosine t minus t is a solution to ty prime equal to y plus t squared sine of t. And I do think the way she addressed this in class was definitely the right way to go. Meaning, you want to show this is a solution to this. So you're going to look at this, and you're basically just going to try and look at the left side and the right side separately and make sure they're equal to each other, which means we have to find y prime. So I'm going to find y prime. So y prime is going to be, let's see, we need to use the product rule here. So it's going to be -1 times cosine of t plus negative t times the derivative cosine is negative sine. Sorry, I'm running out of room here. -1. So simplifying this a little bit, it's negative cosine of t plus t sine of t minus 1. All right, so now we're going to throw things into the formula. So the left side is t times y prime, which is going to be t times all of that. Let's multiply it out. So we're getting, let's see, negative t cosine t plus t squared sine of t minus t. If you really wanted to, you could probably work with this. You could be like, oh yeah, look, there's y right there. So this is y plus t squared sine t. But I think it's easier to just say, okay, let's look at the right hand side. The right hand side is y, which is this, plus t squared sine t. And then we check and make sure they're the same. Let's see, same, boom, we're done. So that's normally how you check to see if something's a solution to a differential equation. Now, I will point out, if you were just given this and you were asked to solve it, that is a whole nother ball of wax, as old people like to say. Yes, solving this differential equation is probably mildly challenging. I don't actually know. Maybe we can try that next time. But we're definitely going to get into talking about how we solve differential equations, and then also looking at how to see if something is or is not a solution. Last thing I want to say before we go, I know she mentioned showing that like the whole, what was the word? Sorry. That a family of functions was a solution to a differential equation. A family of functions just means there's a plus c somewhere, so right where c can be anything. So like she was talking about an example in class. I don't remember exactly what it was, but it was something like how f of x was like, it was like 1 over x plus c was the family of solutions to some differential equation. That just means there's an infinite number of solutions, but they all kind of look the same. Right? They're 1 over x plus 1, or 1 over x plus 2, or, right? It could be, c could be anything. They're all different, but they all look similar to each other. So in case you were curious what that meant, that's what family of solutions means. All these functions that are kind of the same, but differ by a constant somewhere. I should say though, this function and this function don't actually differ by a constant, right? They have different shifts, but the constant is stuck inside the denominator, so it's not like you just add something to it, right? It's a little bit different than just differing by a constant. And actually, that's something else we're going to see as well. That when we're solving differential equations, the constant that we have when we integrate both sides actually is a little bit more important than maybe it's been in the past. So we're going to have to be extra careful about making sure that plus c ends up in our integral. And then we have to treat it with great respect because it actually is important where it ends up